Good morning, everybody, and welcome back to the Crypto Cafe. So today we have a faculty from our group, Dr. Veronika Kuchta, and she's going to talk about proximity gaps in interactive Oracle proofs of proximity. So thank you very much. The floor is yours.
I was afraid of this noise. We didn't have any noise for several days, right? And now, or weeks even. Okay, so welcome to my talk. And for those of you, there are not so many who don't know me, I indeed do research in cryptography, especially post-quantum cryptography, with, at the moment, main focus on post-quantum cryptographic protocols, such as zero-knowledge proofs. So the new phases, have you heard of zero-knowledge proofs before? Yeah. New phases. Okay. Okay. Right. Okay. Yeah. Then I will first give a very brief overview about this, but I'm not really going to talk about how to construct the zero-knowledge proof. I'm actually going to talk about how linear codes such as read Solomon codes are used in this kind of cryptography. The interesting thing, I'm also not going, my presentation is not about code-based cryptography, right? If you hear read Solomon codes, you probably might think, okay, this belongs to the area of code-based cryptography. No, actually, these kind of constructions belong to the area of hash-based cryptography, which is also qualified as post-quantum cryptography. But it's really interesting to see how linear codes, most of the time these are read Solomon codes, are used in such constructions or are useful in such constructions. Okay. So the title was Proximity Gaps in Interactive Oracle Proofs of Proximity. There are many probably foreign words, right? I will start first by introducing such notions like proof systems. So there are many proof systems which are out there. I will start with interactive proof systems, and I will also be talking about probabilistically, very briefly, about probabilistically checkable proof systems, then interactive Oracle proof systems, and then there are also the zero-knowledge proof systems. And then what's the connection between all those information theoretical proof systems to the cryptographic proof systems, which are also known as argument systems. Okay, let's start with interactive proofs. So, first of all, it's a proof system which involves two parties, a prover and a verifier. And the prover is the one who wants to prove some statement to and the verifier is the one who has to verify, right? So it's an interactive proof system is an interactive protocol between the prover and the verifier, where the two parties can interact with each other. So the verifier can challenge the prover, ask some queries to the prover can respond to these queries correspondingly. And in the end, after running in multiple rounds, the verifier would need to verify the proof, right? And so this is the formal definition of such interactive proof system. So a secure interactive proof system has to satisfy two security properties, which is completeness, sometimes it's also called correctness of a proof system, and soundness. And completeness just means that if the prover is honest and runs all the computations honestly, does not try to cheat, right? Then such a prover can convince the verifier to accept the proof, to verify the proof up to a small completeness error. We live in a world which is not ideal. We assume that there also error can happen. And this is like the formal definition for this completeness or correctness property. The probability that the verifier accepts the proof, the output of the verifier after interaction with the prover is 1, that means accepting the proof, should be close to 1, so greater than 1 minus some small completeness error. And the soundness property, here we assume the interaction between a dishonest prover and honest verifier. So a dishonest prover who actually tries to manipulate the proof in some dishonest way, can convince the verifier to accept the proof with only a negligible probability. So this is what it means. The probability that the verifier accepts the proof after interacting with the prover. So these are some other inputs to the protocol, like the randomness is also involved in the proof. X is the actual statement that the verifier has made at the beginning. The probability that the verifier after interaction with the prover accepts the proof, so outputs 1, should be negligible. Actually, he should be a star, so it should be an interaction of the verifier with the dishonest prover, right? Yeah. And I mentioned earlier, so at the beginning when I introduced the title, I mentioned proof systems and then cryptographic proof systems. So while in number theoretic proof systems, we assume that the prover can be computationally unbounded, in cryptography, what we need is that we assume that the prover who interacts with the verifier is computationally bounded. And in this case, we talk about argument systems or cryptographic proof systems, but usually we call them argument systems. So that means in argument systems, we are talking about computational soundness, assuming that the prover is computationally bounded. And if you want to obtain an argument system from an information theoretical proof system, such as, for instance, interactive proof system or probabilistically checkable proof system, I will briefly talk about it on the next slide. What we need, we need these two building blocks. So we take one information theoretical proof system and we combine it with a crypto system, which is usually a commitment scheme, right? A cryptographic commitment scheme. And the combination of these two constructions gives us a complete cryptographic proof system, which we call argument system. Okay, and here I also very briefly want to mention the difference between probabilistically checkable proof systems and zero-knowledge proof systems. So they are known as those paradoxical proof systems. And why this is the case? It's because of that. So in probabilistically checkable proof systems, we assume that randomized verifier has access to proof oracle. And in order to accept the proof, the verifier doesn't need to read the entire proof in its entire length to verify each position step by step. So it's already sufficient to verify, for the verifier to just read a few positions of the entire proof to be convinced whether the prover made a correct statement or not. This is what defines probabilistically checkable proof system. And of course, the security properties are the same as for interactive proof systems. A secure probabilistically checkable proof system, abbreviated by PCP, satisfies completeness and soundness, meaning exactly the same. And now, zero-knowledge proof system is another paradoxical proof system in which the prover can convince the verifier of knowing a secret information without telling what this secret information is, right? So this the prover doesn't leak any knowledge about the secret to the verifier. They can build a proof in such a way that in the end the verifier can indeed be convinced that the prover knows a secret which satisfies some particular statement. The easiest example, for instance, if you look at the discrete logarithm, h, for instance, is equal to g to the x. And let's say h and the base g is public information, right? And x is what is secret, what is only known by the prover. they can build a cryptographic protocol in just 2 moves, and the verifier can indeed be convinced that the prover knows the exact secret, such that this statement is satisfied. H is equal to G to the power of some secret. So this can be done by probably most popular protocol is the Schnorr's zero-knowledge protocol. And so basically, this is the idea behind zero-knowledge proof. And of course, a secure zero-knowledge proof satisfies the properties of completeness, meaning the same as for the other proof systems, and soundness. The soundness means that dishonest prover can only convince a verifier with a negligible probability. And completeness means as long as the prover is honest, then such a prover can convince the verifier with a probability of almost 1, up to some small completeness error. And there is an additional property which we require in zero-knowledge proof systems. This is the zero-knowledge property, meaning that from this in public transcript, so this is what is publicly transferred between the prover and the verifier. The prover first makes the first statement, sends it to the verifier can challenge the prover, so all of this transcript is public. And then in the end, after receiving the challenge from the verifier, the prover can respond correspondingly to the prover. And zero-knowledge property means that from this public transcript, no information about the actual secret will be leaked. This is what the zero-knowledge property means. Okay. Okay, now we are moving closer to the actual topic of this talk, but it's still not exactly the end result. So the next proof system is the interactive proof, the Oracle proof system. Later, I will be talking about interactive Oracle proof systems of proximity. Right? This is what we are indeed interested in. Interactive Oracle proof systems are just a combination of interactive proofs and probabilistically checkable proofs. Right? As you remember, interactive proofs allow interaction between the prover and the verifier, and probabilistically checkable proofs are not interactive. Right? The randomized verifier only has access to some to the proof oracles, and can query the proof oracle on only a few positions of the proof. Here, an interactive Oracle proof systems involves interaction between the prover and the verifier. And so this is a combination of the interactive proof system and the probabilistically checkable proof systems, which is run in this case in K rounds. And the security properties are, of course, also the same as for IPs and TCPs, namely completeness and soundness. Once again, completeness means as long as the prover is honest, such a prover can convince the verifier of the statement with an acceptance probability of 1. And soundness property, dishonest prover who doesn't know the actual information which belongs to the statement can convince the verifier only with a negligible probability. And here I want to briefly talk about the connection of these information theoretical proof systems to cryptographic proof systems, which are the argument systems. Right? So those interactive Oracle proofs are very widely nowadays used in cryptographic argument systems. And those cryptographic argument systems, they are also known as ZK snarks. This stands for zero knowledge, decay. SNARK stands for succinct, short proofs, right? Non-interactive, so there is no interaction between the prover and the verifier. Arguments of knowledge, meaning that the prover's power is bounded, right? Okay, how are those ZK snarks obtained from those mathematical, from information theoretical proof systems? So it's obtained from a combination of a cryptographic tool, as I mentioned before, which is a commitment scheme, and an information theoretic proof, like an IOP, interactive Oracle proof. So, but after we have combined interactive oracle proof with a commitment scheme, we do not obtain a non-interactive oracle proof, right? For instance, you know now that an interactive oracle proof is interactive. Interactive oracle proof is an interactive system, right? And so if you combine an interactive system with a commitment scheme, we have SARC, right? We don't have the M, we don't have the non-interactiveness yet. But to convert this SARC system into a SNARK, into a non-interactive cryptographic proof system or argument system, we apply a technique which is very widely used in cryptography to turn interactive systems into non-interactive protocols. This is the G-action transform. Okay. So the commitment scheme, or it's in case of combination with IOP, it's a polynomial commitment scheme, enables to run polynomial interactive oracle proof succinctly, meaning that the proof, which is output at the end by the prover, is a short proof. And the prover does need to send the actually a whole polynomial to the verifier. In this case, the prover just needs to send a commitment, a short commitment to the whole polynomial. Another kind of cryptographic proof systems are STARKs and ZK STARKs. These are interactive arguments of knowledge, which are using public randomness. The T here instead of M stands for transparency, meaning that the randomness which is used between in the creation of the proof is publicly known. The really good thing about starts, ZK starts, is that they're actually up to 10 times faster than ZK snaps. And this is, which is very important in, especially in blockchain applications, but also other applications like e-voting schemes and others. Okay, and a generalization where researchers were looking at later. The generalization of IOPs, interactive oracle proofs, is an interactive oracle proof of proximity. So here we assume again that the randomized verifier can interact with the prover, has access to the proof oracle, and if a verifier in the end accepts a proof, then that also means that the statement which was made by the prover at the very beginning of the protocol belongs to a particular kind of, is close to code word or to some linear code. I will later mention to you that nowadays everyone is using cryptographic codes because of their simplicity or whatever. Okay, so this is the definition. Let's look a little bit closer at the definition of IPPs. It's again, it's an interactive proof system. It's run in R rounds, and it's run actually in R+1 rounds, and it involves an error correction code, right? An error correction code, which is, as I mentioned, is usually the read normal code. It has soundness error sigma. And with respect to the distance measured, which is usually the Hamming distance, and interactive oracle proof is defined in such a way if the following three properties hold. And the three properties are the following ones. So additionally to the completeness and soundness properties, which have all the other proof systems, right? This interactive oracle proof of proximity also has this first message format. The first message which is sent from the prover to the verifier is this code word of linear code, Solomon code. And completeness property is now defined a little bit slightly different. So if the distance of the first message from the linear code, basically if the first message is a linear code, is a read Solomon code, right? So the distance is 0. Then the probability that the verifier accepts such a proof, right, should be equal to 1. So that means if the first message which was made by the prover in the protocol was indeed a read Solomon code, then the probability that the verifier accepts such a proof should be 1. Now, soundness property. Remember how it was defined for the other proof systems. So if the prover was malicious, then the probability that a malicious prover manages to convince the verifier of a statement, of the correctness of a statement, should be negligible, right? So what does it mean here for IPPs, interactive oracle proofs of proximity? So if the first message made by the prover, the claimed message, right, is actually far from a Reed-Solomon code, right? So the heading distance of the first message is greater than delta, is far from a linear code like the Reed-Solomon code. Then the probability that the verifier rejects such a proof should be greater than negligible. Okay, so the actual problem that we are dealing here with is the proximity problem. And as I mentioned, such interactive oracle proofs of proximity, they are usually instantiated with Reed-Solomon codes. So I will present here the Reed-Solomon proximity problem. In the Reed-Solomon proximity problem, we assume that the verifier has oracle access to function f, which maps from a domain to a finite field. And S is just the evaluation of an element. Then the problem for the verifier is to distinguish with large confidence, and in best case with small query complexity, whether this message F is a Reed-Solomon code, or whether F is far from a Reed-Solomon code, or delta far in heading distance from all code words. Okay. I already talked about it, Reed-Solomon codes, it was also in the title of my talk. So one of the prominent linear codes, which is used to instantiate such an IPP, is the Reed-Solomon code, which is defined as follows. So if you are given a list of distinct elements, alpha 1 to alpha n, then the Reed-Solomon code of block length n and rate k over a finite field Q with evaluation point alpha 1 to alpha n is defined as the set of evaluations of polynomials in alpha 1 to alpha n. And the degree of polynomials there are smaller than k. And now, so I'm going to present a widely known IPP from Reed-Solomon codes, which is the fast Reed-Solomon based interactive oracle proof of proximity. Of course, it's abbreviated as TRI. And the construction of such a protocol looks as follows. So we will have now a concrete construction of an interactive oracle proofs of proximity from Reed-Solomon codes. And this tool in the end can be used in combination with some polynomial commitment scheme to construct those cryptographic protocols which are known as argument systems, right? So this is now important to see the construction of such an IPP. So let's imagine that L is just L0 is a subset of a finite field F. The length of L0 is N, and the prover's claim is that the first message, right, F0, the first message of the prover, which maps the domain L0 to F. Yeah.
Is L0 is a subset of the finite field?
Yeah.
So the finite field has to be bigger, has to be like bigger than the length of the evaluation?
Yeah. Yeah. So the prover's claim in the protocol, the prover claims that this F0 is a Reed-Solomon code, right? And this is what the verifier has to verify in the end. And if F0 is a Reed-Solomon code, that means that F0, by definition of Reed-Solomon codes, is an evaluation of some polynomial P0 from this polynomial ring, where the degree of the polynomial is upper bounded by the rate to the number of elements of the domain. Okay, the task for the verifier now is to distinguish whether F0 is is congruent to some low degree polynomial P0, or whether F0 is far from all polynomials of degree rho times 2 to the n. And the idea which is used here was actually borrowed from inverse FFTs. So if F0 is indeed congruent to some low degree polynomial P0, then it means that there exist two other polynomials, P01 and P11. So you will see now in this concrete example what I mean by this, where the degree of each of those polynomials is smaller than a half of the initial degree. Okay, so let's imagine F0 of x was equal to this polynomial P0, right? And which looks like that. It's a polynomial of degree k. So what we can do, we can split this polynomial into two parts. All monomials with even degree will be put into the polynomial P01, right? And all monomials of odd degree will be put into polynomial of P11 multiplied by x. So basically, this is a polynomial, the red part here, we can see it. This is a polynomial P01 in y, where y is just equal to x squared, right? And here, so if from this green part we factor out x, we have again a polynomial P1, we have a polynomial P in y, where y is equal to x squared, right? Okay, so what has happened here? We mentioned earlier. So if F0 is indeed congruent to some low degree polynomial, then there exists such two polynomials P0, so the red one, P01, and the P11, the green one, with degrees for sure smaller than a half of the initial degree. Right? So the degree of each of those polynomials is smaller than a half of the initial degree. So what we actually have managed by now is to reduce the problem from degree rho to the n to a problem which gives us polynomials of degree which is a half of the initial degree. So now if you set Q0, if you define a polynomial Q0 to be equal to x0, then we can see from here that P0 of x is congruent to a polynomial Q1xx. So Q1xx is this part here, right? Modulo y minus Q0 of x. And the degree of this polynomial Q1, so the frank one, in x is of course smaller than 2. And the degree of the polynomial, the frank one, in y is smaller than a half rho 2 to the n. Okay, so what can we say about the map which maps x to this polynomial Q0? And Q0 is just defined as a polynomial which is equal to x to the x squared, right? So this map is of course a 2-to-1 map on L0, and the output of this map is a multiplicative group of order to the n minus 1. And we denote this output set by L1. So what in the next step, the verifier would sample x0 and request from the prover to send a request to give him evaluations, to give him new polynomials, f1. But first of all, for each x0 and y, now from this domain L1, the polynomial Q1, remember from the previous page, it's the frank one. If you evaluate this polynomial in x0 and 1, so this polynomial can be completed just by querying two queries to the original polynomial x0, to the original oracle, proof oracle x0. And these two entries are just the two roots of the polynomial y minus q0. Okay. So basically, the verifier's task in this protocol is the following. Verifier samples x0 and requests a polynomial f1 from the prover. And this polynomial f1 is just the evaluation of q1 in x0 on L1. So it holds now that f1 is also a read-Solomon code over the domain L1. And the last task for the verifier would be to run the consistency test on the polynomials f0 and f1. And this is done as follows. So basically, the verifier has to check that F1 has been computed correctly. If the prover knew F0 and the claim initially was done correctly, that F0 was a read-solver code, right? And this is done as follows, this consistency test. The prover, the verifier would sample a uniform Y from the domain R1, and S0 and S1 should just be the roots of this polynomial, Y minus X squared. And then the verifier would query from the prover the evaluations of the polynomials F0 in S0 and S1, and the evaluation of polynomial of 1 in Y. So if you assume that alpha 0 is the output of F0 S0, alpha 1 is the output of F0 S1, beta is the output of this one, then what the verifier can do is interpolate a line through these points, right? And then this will give the interpolation of a line to the 2 points will give the verifier polynomial of degree 1, and which satisfies exactly this property, right? And the verifier accepts the consistency test, meaning that F0 and F1 was computed correctly, as long as F0 was a reasonable code. So the verifier would accept if and only if P now evaluated that F0 is beta, otherwise the verifier rejects it. So this kind of technique here allows us to reduce a single proximity problem of size 2 to the n to an analog proximity problem of size 2 to the n minus 1. So if you repeat this procedure several times, you can see that we will be able to reduce the proximity problem up to the size of 2. And here a little bit more about how this FRI protocol in the end is put together. So in the FRI protocol, the verifier performs all the queries to the prover only after the prover has sent all of those polynomials F1 and Fr, which are computed in all R rounds. And then the FRI protocol is run in two phases. The first phase is the commit phase, and the second phase is the query phase. So in the first phase, the prover basically commits to the initial polynomial, right? And then reduces it to lower subdomain, computes a new polynomial, and so on and so on. So basically, the first phase is called the commit phase. It involves R round. And at the beginning of the ith round, the prover has already sent F0 to Fi minus 1 proof oracles, right? This function F0, polynomials F0 to Fi minus 1. And during the ith round, the verifier samples Xi, and the prover responds by sending the next Fi. And then during the second phase, which is called the query phase, the verifier applies the round consistency test. So when the verifier sends those two queries to verify that Fi and Fi minus 1 they're computed correctly, are consistent. Okay. So to save query complexity and to improve the soundness of this IPP protocol, the query made to Li is used basically to use the consistency of the two functions, two polynomials Fi minus 1 and Fi. And also the consistency of the function Fi and Fi plus 1. And then, so this was the idea of the IPP test, IPP protocol from read-Solomon code. And after we have constructed a proof system, what we need is to prove that its security properties, right? So we need to prove that it's correct or complete, and that it is sound. And here it's actually interesting where some coding theory comes into the play. In order to prove the soundness of IPP, we have to pay attention to the following. So we have seen before that the proximity testing, the initial proximity testing problem which was defined initially over a large domain, was reduced to a proximity testing problem over significantly smaller domains. So the cost of the verifier in this protocol depends on the query complexity, which, as you remember, the round consistency test requires several queries sent to the prover responds to those queries. So the cost of the verifier depends on those queries in the round consistency check to check the consistency of Fi and Fi plus 1. And another cost is the reduction in distance. So basically, this reduction of a larger proximity testing problem to a smaller proximity testing problem leads to a reduction in distance, of course, and this affects the soundness of the protocol. So here, if you assume that F0 was delta 0 far from all code words initially in the relative Hamming distance, then F1 is delta 1 far from all code words. So basically, delta 1 is depends on delta 0. And larger values of delta 1 imply higher and better soundness and smaller communication complexity. So that means if you want to study soundness property of interactive oracle proofs of proximity, what we need is to study proximity gaps of codes, in this case of Reed-Solomon codes. So we see that soundness security of IPP heavily depends on this parameter delta, right? And this is what leads us to this definition of proximity gap. So first of all, that's a formal definition of a proximity gap. So we say that, for instance, a linear code C displays a delta epsilon proximity gap with respect to the Reed-Solomon code, for instance, under a distance, like the Hamming distance, if every code word satisfies exactly one of the following properties. So either the code word is less than delta far from Reed-Solomon code. So either this property, either this probability is equal to 1, or the probability is just negligible, right? So that means the value S is far from Reed-Solomon code. So in this case, delta is the proximity parameter and delta is the error parameter. And so there was a paper by Eric Vanderthorn plus Titko Party defining proximity gaps for Reed-Solomon codes. So they were studying those proximity gaps. And this is a theorem which they found. So if we consider a Reed-Solomon code which is defined over domain D with block length n and where rho, where delta lies in this interval, and epsilon is the error parameter, then this error parameter can be computed in two ways. So if delta, if this proximity parameter lies in the interval, so in the first half of this interval from 0 to 1 minus rho over 2, then the error parameter is the decoding error is defined like that, n over q. If the delta parameter, proximity parameter lies in the second interval from the half up to the upper bound, then the error parameter is defined by this Johnson bound. So the proximity gap, as you have seen before, has these two parts. Each part depending on whether delta lies in the first interval or in the second interval. And so the first proximity gap holds only below the unique decoding radius. And so up to 1 minus square root of rho over 2, right? But it has a smaller error parameter. And the second part, as you've seen, it holds for proximity parameters up to the Johnson-Goswami-Sedan bound. But it has a larger error bound. So basically, maximum proximity parameter for which the proximity gap theorem holds coincides exactly with the Johnson-Bruce-Lamison boundary decoding bound. In that paper, it was conjectured. It is actually a really interesting question, but it is a conjecture that this theorem, proximity gap for each normal holds even for larger proximity parameters, for larger delta, up to the capacity 1 minus rho. And remember, as I mentioned before, larger delta means better for the soundness property of our IPP protocol, right? So what we need is to analyze linear codes and their proximity gaps, whether we can improve this current result which exists right now. So right now we have proximity gaps which are defined up to this bound. So the question is, if we mention to improve this bound, so if you mention to define proximity gap up to the bound 1 minus rho, then that would lead to a significant improvement of the soundness of IPP protocols, which would immediately lead to an improved soundness of ZK starts or ZK snarks, right? Because as you know, ZK snarks and ZK snarks are built from IPPs plus some commitment scheme. So basically, the soundness of ZK snarks, the cryptographic protocols, is directly depends on the soundness of the underlying IPP. Okay, now let's look now at I already mentioned this, right? But this was my next slide. What is the connection to IPP? So we know IPP protocols. We assume that the verifier has access to potential vectors like U0 to UL, and the soundness of IPP protocol requires that each vector from this batch of vectors is close to Reed-Solomon code in Hamming distance. So to argue soundness, we want to show that even if a single UI from this set that are given to the verifier is delta far from a Reed-Solomon code, then it would automatically mean that a randomly chosen UI is also delta far from a Reed-Solomon code. Indeed, in one of the previous results, it has been shown that whenever a single UI is delta far from a Reed-Solomon code, then nearly all samples are not just randomly chosen U prime, but all samples U prime are at least delta far from a Reed-Solomon code. So it means that leads to a degradation of the proximity parameter by a factor of 2. So that's why we need indeed to study this proximity parameter maybe also for other linear codes. So we need to look into instantiations of IPP protocols from other linear codes, maybe Reed-Miller codes. Or I will later show what is our approach. So this is a work which I'm working on in collaboration with coding theorists, and so what we are trying to prove is a proximity gap for folded Reed-Solomon code. We know that folded Reed-Solomon codes are least decodable up to the proximity parameter delta 1 minus rho minus some small epsilon, right? This brings us already to what we actually need, right? In ideal case, we want this proximity parameter to be improved up to this form, 1 minus rho. Okay. Basically, remember now the pri-IPP protocol. The messages which were sent from the proof of the verifier, they looked something like that. Yeah, a polynomial plus z multiplied by another polynomial. So now we can define this proximity gap theorem specifically for the IPP protocol, right? So let's assume that we are given these parameters as before. We use the Reed-Solomon code, Q and K, and the block length of the Reed-Solomon code, rho is the rate. So they are all defined as before. And then for two elements U0 and U1, if delta lies in this interval, right, then the probability that line which was interpolated from these two points is close to a Solomon chord, right? So the distance of the line from a Solomon chord is smaller than delta. The probability should be bigger than negligible. If this is the case, then we can say then there exists a dense subdomain in D, which is D prime, and there exists this agreement that V0 agrees with U1 and V1 agrees with U1 on all elements of D prime. So the idea to prove such proximity gap theorem or this correlated agreement theorem is not simple at all. So the proof was done in this proximity gap paper by Eli Ben-Zasson. I think it runs over 15 or 20 pages. But the idea, just to summarize what is going on there, is I just bring you a few points. So what we need to do in order to prove the proximity gaps, in order to compute the error bounds for the proximity parameter up to a line in this interval, we work with the function field k, which is fq in z, with a formal variable z. And then what we do, we study various received words, u0 plus zu1 for the Solomon chord v. But we consider formally received word w, which is u0 plus capital Z u1. And what we need to do is, if you want to show that this formally received word is close to a Solomon chord word, then it is sufficient just to show that u0 and u1 are both close to the Solomon chord. That's the actual idea of the proof. And the proof strategy involves these various steps. Well, maybe go quickly over them. So what we need to do is to run a decoding algorithm for read Solomon codes on the received word W, which is defined like that, and then analyze the execution of this algorithm to show that it indeed succeeds to find close or nearby read Solomon code words. So if you assume that the received word was u0 plus zu1, which is defined from the domain delta to k, and k is defined like that, which is a large field. The main goal is to find a nearby low degree polynomial p of x of this form, right? With each pi from this polynomial ring. The next step would be, since we are running the decoding algorithm, we need to run a decoding algorithm and then analyze the decoding algorithm. So we need each decoding algorithm runs like usually two steps: is the interpolation step and the root finding step, right? So the next step would be the interpolation step, where we run the decoding algorithm in order to interpolate a polynomial q in x and y, such that q evaluated at x and where y is the received word, w in x, is equal to 0. And okay, then there is a substitution step. So there are several steps involved, as I said, and the proof is pretty involved, over 15 to 20 pages. But so it uses various techniques, especially tensor weighting for the factorization of the root finding step. And in the end of this proof, we managed to demonstrate that there exists some factor y minus p of x of that polynomial q, interpolated polynomial, which we have interpolated in the interpolation step, such that p of x has a high agreement with the received word w. And all coefficients are linear in Z. So if we succeed basically to run through all those steps and to find the existence of such a factor, then we can conclude that the correctness of the proximity gap theorem. And okay, as I mentioned before, the idea in this project is to look into how can we improve the soundness of those IPP protocols. We know that soundness can significantly be improved if we manage to increase this delta, proximity parameter delta, right? Is there a way to improve this proximity parameter? One way would be to prove already this proximity gap theorem for each Solomon codes up to this delta parameter, 1 minus rho. It's a conjecture. I don't know if it's that easy to prove. But another idea is to use other codes instead. There is already an instantiation of IPP from folded in Solomon codes. So that means we have to study the proximity gaps for folded in Solomon codes, which are defined like that. And that would lead to basically a new proximity gap theorem, still relating these current error parameters. And as you can see, data parameter manages to be improved up to the bound 1 minus rho minus some small epsilon parameter. These errors I cannot confirm at the moment, but we are expecting them to be definitely better than the error parameters in the proximity gaps for simple epsilon codes. So in order to prove the above theorem, as we have seen before, for folded epsilon code, we would need to analyze decoding algorithms. And there exists already a decoding algorithm for folded epsilon codes, which is valid up to about 1 minus rho minus epsilon. So what we need to do is to run this decoding algorithm, analyze it each step by step, and see whether we indeed manage to complete the analysis successfully. So we are expecting an improved error parameter, which would lead to an improved soundness analysis of IPP, which at the same time means that we would indeed have better snarks, since we know that snarks or starks can be obtained from IPP with a better soundness analysis. So it's like one direction of this, how linear codes can be used to improve soundness analysis of hash-based ZK snarks, right? Another open question. So as I said, what has been used so far in all of those constructions of ZK snarks from IPs or IPPs, those are only read Solomon codes. No other codes has been explored yet. Why not? So I would be interested to look into read Miller codes, for instance, or I don't know. Maybe you can tell me more, right? And then, so I think there is a lot of work still to be done, and a lot of new results can be expected. That's actually my presentation. So.
Thank you very much. I have a question. When you were putting the first result on the decoding bound and say that these two intervals, in the second one there was some bigger of 1 and so on, some estimates, right? So is there a formula for that, or is there some kind of bound that you have for
there is no
the epsilon?
There is no direct formula. So this part, you mean this corresponds to down bound, right? This one.
This one, yes.
Yeah, no, it doesn't follow a complete formula. It follows this is derived from everything is derived from the degrees of the interpolated polynomial of the factorization factors of the polynomials of Q.
So, but you have an exact thing.
This is an exact thing. Yeah, you have an exact thing. It's not just all.
Okay.
The kind of classical continuum bound, like very standard thing.
Yeah.
Yeah.
I am more curious because again I could follow the but like this proximity problem is kind of like a decoding problem, right?
Mhm.
So
It is a decoding problem, yeah, this is the main problem that we have to solve.
essentially, if you can decode, you can solve this.
Yeah.
This proximity. So I think if you can use some classes of code that have like larger decoding ranges, then they should
Mhm.
perform better than this. And
That's what I'm expecting.
I don't know if
That's-
they didn't look at them, but of course, there's something very clever about using this algorithm because you can treat polynomials as code words. They have kind of like a compact description, but
Yeah,
I wonder what happens if you just use a normal code to code words that are vectors instead of polynomials, like, and then like you just look at how to test things. Like, but I'm thinking completely different codes, like LDPC or,
yeah, yeah, yeah.
you know, like then this may work a lot better, so.
It is possible. I talked to the author, Benson, about this. So why read-only codes have you tried, for instance, folded read-only code or other read-only code? He said, yeah, I mean, we like picked read-only codes because they're just the simplest to deal with,
Yeah.
and that's all. But of course, there might be better results, but like each paper involves such a deep analysis of problem. They have a good result, and then
Yeah.
they leave the other work maybe for the future researchers.
Okay. I just, were you part of this publication?
Hmm?
Were you part of this publication?
No, I'm working now on the new direction, proximity gaps for folded read-only codes. So this publication is done by Benson, this one. Benson, this is proximity gaps by for read-only codes. Okay.
Thank you very much. Yeah.
You in 2 weeks.
Mhm.
I suspect these people, I know you are shy, but the other ones I know by name. They're not,
This one is a proximity.
yeah, but the it's still kind of very traditional, like they do this, it's all like this traditional.